Hello everyone, welcome back to Coding Charms. This is the video 10 in our sliding window pattern series, and in this video we are going to be solving the problem longest subarray with ones after replacement. This is tagged as a hard problem, but it is actually an easy problem if you have watched my previous videos. So if you haven't watched those videos, I would highly recommend you to watch those videos before this video. If you watched those videos, you can actually solve this problem all by yourself. So without any further ado, let's get into the problem statement. So we are given with an array containing zeros and ones, and we are allowed to replace no more than k zeros with ones. So we can replace at most k zeros with ones in our array. And we have to find the length of the longest contiguous subarray having all ones. Okay, we can replace at most 0 k zeros with ones, and we have to find the longest contiguous subarray having all ones. So let us understand the problem a bit more by seeing the example. So in this example, we are given with this array and the k value is 2. The k value is 2 means we can replace at most two zeros with ones. So let me take the pen. Okay, so we have this 0 1 1 0 0 1 1 0 1. We can replace two zeros with ones, right? So we can start over here. We can consider this array 0 1 1 0, or else we can start over here and consider so far 1 1 0 0. We cannot add this 0 because then our zeros in our subarray will be 3. We can only replace 2. So we consider 1 1 0 0. The longest I can see is starting from here. So 0 1 1 0 1 1. So we can replace this 0 with 1, this 0 with 1. Then the length of the longest window will be 1 2 3 4 5 6. So we return 6. And in the next condition, next example, we are given with 0 1 1 0 0 1 1 0 1 1 0 0 1 1, and the k value as 3. So we can replace at most 3 zeros with ones. So here, if we take here, we can start over here. Where is my pen? Okay, we can start over here and we can go till here. We can replace this 0, and this 0 with ones. Then the length of the window will be 4. Or else we can start over here and we can go till here. We can replace this 0, and this 0 with ones. Then the length will be 6. Or else we can start over here and then we can go till the end, right? We can replace this 0 1, this 0 2, and this 0 3. If we replace all these zeros, then the length will be 1 2 3 4 5 6 7. And we can also consider this. If we start over here, then we can go till here. We can replace these 3 zeros and all these are ones. So 1 2 3 4 5 6 7 8 9. So the longest I can see is of length 9. So we return 9 as our answer. So let's see how we can solve this problem. So let us consider the example. The first example 0 1 1 0 0 0 1 1 0 1 and 1, and the given k value is 2. So what will be the naive or the brute force way of solving the problem? In the naive way, what we can do is we can generate all subarrays. We can generate all the subarrays and then we can count the number of zeros in each subarray. We can count the number of zeros in each subarray, and if the zeros count is less than or equal to k, then we know that the subarray is valid and a potential answer subarray. If this is the condition, then we calculate the length of the subarray. We consider the length of the subarray and we keep track of the maximum length variable. We keep track of maximum length variable, which consists of the longest length subarray, the longest length of the valid subarray, and we finally return this maximum length. What will be the time complexity of this approach? To generate all the subarrays, we keep track of 2 loops. We take 2 loops. We consider all the possible ij values and we take the subarrays. So to generate all the possible subarrays, we take two nested loops, so the time complexity will be O of n square, and to count the zeros we iterate over the subarray, so it adds up another n complexity. So in total the time complexity will be O of n cube. What will be the space complexity? We don't need any other fancy values, we just need a zeros count value and length value and maximum length variable. So the space complexity will be O of 1. The time complexity is O of n and the space complexity is O of 1. Can we optimize this? Let's see. In the previous videos, we have seen that we can apply sliding window approach when we have to find something in a contiguous subarray or a substring or a sublist, right? In this problem as well, we have to find a longest contiguous subarray which contains all ones, and we can replace at most k zeros with ones. So here also we have to find the longest contiguous subarray. So we can use the sliding window approach. And we know that sliding window has two variations. One is the constant length sliding window and the variable length sliding window. In this problem, we have to find the longest contiguous subarray. So we don't know what is the length of the subarray. So in basically the subarray or a sublist or the substring will be the sliding window. So we don't know the length of the sliding subarray prior. We have to find it. So it comes under the variable length sliding window problems. So we can apply variable length sliding window pattern to solve this problem. Let's see how we can solve it using variable length sliding window. Let me write down the example again. 0, 1, 1, 0, 0, 0, and 1, 1, 0, 1, 1. And we know that k value is 2. We can replace at most 2 zeros with ones. Okay, so in variable and sliding window patterns, as we have discussed in the previous videos, if you haven't watched the previous videos, I recommend you to watch them before, because we use almost all the concept which we have discussed in the previous videos here. So this will be a very easy problem if you watch those videos. So basically in variable and sliding window patterns, we use two pointers, start pointer and the end pointer, to keep track of the window itself, right? We don't know in variable and sliding window patterns where the window starts and where the window ends, what will be the length of the window. So to keep track of that, we use start and end pointers, unlike the constant length sliding window patterns, because if we keep track of one thing, then we can calculate the other thing using the length of the window. If we keep track of the start in constant length sliding windows, we already know the length value they have given us, so we can add plus k and we can get the length, we can get the window. Unlike here, we have to keep two pointers S and E to keep track of the variable and sliding window. And in this problem, what we have to do, the problem asks us to find the longest contiguous subarray with having all ones, and we can replace at most k zeros with ones. So we should have a count of zeros, right? So let us take a variable to keep track of the zeros count in our window or our subarray. So let us name it as zeros, and we should also have a variable to keep track of the maximum longest length subarray which has all ones. So let's take it as maximum length variable and start the execution. So what we do here is, to solve this problem, we can expand the window. We can expand the window when the window is valid. When will be the window valid? When the count of zeros in our current window is less than or equal to k. Because if they are less than or equal to k, we can replace all the zeros with ones. So this is the condition which determines if our current window is valid or not. We expand if our window is valid. How do we expand? We increment the e pointer and we expand the window. Because we want to find the longest. To find the longest, we try to achieve the longest window by expanding the window, right? And if when do we shrink the window? If our window is invalid, then we shrink the window to make it valid again, right? To make it valid, we shrink the window. And how do we do that? By incrementing the s pointer. Okay, so let us see this in execution. Let me remove this. Okay, remove this as well. Let's start the execution. So firstly, S and E pointers are at 0th position. Let me write down the indexes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now let's start the execution. We are at 0th position. So we expand our window. So we add 0th position to our subarray, and we increment the zeros count as our current value is 0. We increment the 0. Initially this will be 0 and this will be 0 as well. So we increment the zeros to 1, and now what we do is we check if the current window is a potential answer window or not. How we check? The condition is right. Let's write down the condition over here. 0 should be less than or equal to k. This determines if our window is valid or not. So currently 1, we have zeros as 1 and which are less than or equal to 2. So the window is valid. Now we calculate the length of the window. To calculate the length of the window, we use the formula. Let me write down here. Length of the window, use formula E minus S plus 1. This gives the length of the window in variable and sliding window pattern. Okay, so our E value is 0, S value is 0 plus 1. Our current window length is 1 and maximum length is 0. So we take the maximum of length, current length and the maximum length, and we update the maximum length. So we make it 1 in this case. So let me erase this. And now the window is valid, so we move E pointer forward. Now we are at first index and the value is 1. We don't have to increment zeros, and we now check the window is valid or not. And the zeros is 1. The number of zeros is 1, and which is less than or equal to 2. The window is valid. Now we calculate the length of the window. E minus S plus 1. 1 minus 0 plus 1 equal to 2. This is the current length and the maximum length is 1. We update the maximum length with the current, maximum of current and maximum value. Now the maximum length will become 2. Okay, and now we move the E pointer forward, 1 step forward, and now we are second index. The value is 1, so we don't increment the zeros. Again our window is valid. 1 minus 1 is less than or equal to 2. We again calculate the length of the window. E minus S plus 1, 2 minus 0 plus 1, 3. We update the maximum length because 3 is greater, 3. And now again the window is again valid, so we move E pointer 1 step forward. Now we are at third index and the value is 0. So we increment the zeros. 2 zeros now will be 2, and 2 is still less than or equal to 2. The window is valid, so we calculate the length of the window. 3 minus 0 plus 1. The length of the window is 4. So we update the maximum length with the 4. Okay, so now the window is valid, so we again move the E pointer 1 step forward. Now we are at fourth index with the value 0. So we increment the zeros value. Now the zeros count is 3. So now 0, 3 is less than or equal to 2? No. 3 is not less than or equal to 2. 3 is greater than 2. So the window is invalid. Now what we do is we shrink the window, right? Now what we do is first we take this value. If we shrink, we move the S pointer forward, then 0 will be removed. So we decrement the 0. Because this is 0, we decrement zeros. So zeros will become 2 now, and we move S pointer forward, and we remove S pointer forward and we check again if the window is valid or not. So the current window zeros are 2 and 2 is less than or equal to 2. Now the window is valid. Now again we calculate the length of the current window. 4 minus 1 plus 1, which will be equal to 4. Maximum length is also 4, so we do not consider it, we do not update it. So since our window is valid now, what we do? We move our E pointer forward. Let us move our E pointer forward. Now again we are at fifth index with value 0. So we update zeros count to 3. And again 3 is not less than or equal to 2. So our window again became invalid. So we move the S pointer forward. And this value is 1, so we don't have to decrement zeros. We only have to decrement zeros if the value is 0, right? And now we again see, again this condition 3 is less than or equal to 2. So the window is again invalid. So we move the S pointer forward. Okay, we move the only S pointer forward. And now we are at third index. Third index value 0. So we decrement. Okay, third index value 0. And after incrementing, yes, we again check if this window is valid or not. So again, this window is not valid since 3 is less than or equal to 2. So what we do now, again, we move the S pointer forward. Now we are at index 4. Now see, we have moved one step and we have removed 0. So we have to decrement 0 as well. So zeros will be now 2. And we are at fourth index and number of zeros are 2 now. 2 is less than or equal to 2. Now the window is valid again. Now what we do, we calculate the length of the window, 5 minus 4 plus 1, which will be 2. Maximum length is 4. So we keep 4 as it is. And now since our window became valid, we move our E pointer forward. Now our E point is at index 6 with value 1. So we do not increment the zeros, and we calculate if the window is valid or not by checking the condition 2 less than or equal to 2. The window is valid now, so we calculate the length. 6 minus 4 plus 1, 2 plus 1 is 3. So the current length is 3 and maximum length is 4, so we do not update it. And the window is valid, so we move our E pointer one step forward and we are at the index 7. Index 7 value 1. We do not update the zeros, and we again at the same condition, 2 is less than or equal to 2, and now the end pointer is at 7. 7 minus 4 plus 1, now it will become 4. Current length is 4, maximum length is 4. We do not update it. Now what we do, we move our E pointer one step forward, and now we are at the index 8, value 0. So let me erase this, and now we are at 8th index and value 0. So we increment the zeros to 3. Okay. Now we check the validity condition. 3 is less than or equal to 2. No, it's not. 3 is greater than 2. So our window again became invalid. We have to make it valid by moving the S pointer forward. So we move the S pointer forward, and since the previous value is 0, we decrement zeros to 2. Now 2 is less than or equal to 2. Again our window became valid. We calculate the length of the window. 8 minus 5 plus 1. So 3 plus 1, 4. Maximum length is 4. So we do not update it. The window is valid. So we move the pointer forward now. And we are at the index 9. Index 9 value 1. So we do not increment zeros. Now 2 is our value. Zeros count is 2. So 2 is less than 2. And we are ending pointer is at 9. 9 minus 5 plus 1 is 5. So we update the maximum length with 5. And since our window is valid, we move the pointer forward to 10th index, value 1. So again, the same condition. Let me erase this. So we check if the window is valid or not. 2 is less than or equal to 2. The window is valid, and we take the length. 10 minus 5 plus 1, 6. So we update the maximum length with 6, and now the window is valid. So we try to move the E pointer. We try to move the E pointer forward, but we reach the end of the list or array. So we stop the execution here, and what do? We return the maximum length as our answer. So this is the answer 6. So what is the subarray? This is the subarray. We can replace this 0 and this 0 with 1s to get the longest contiguous subarray having all 1s. What will be the time complexity of this approach? So we have S pointer and E pointer. Both of them iterate over the array once independently. So the time complexity will be O of n. And the space complexities, we are keeping track of 2 variables, zeros and maximum length, and some S pointer and E pointer. So the space complexity will be O of 1. Since we are not using any fancy data structures, we are only using the constant variables. So we have reduced the time complexity from O of n cube to O of n using the sliding window approach. So I hope you have understood the approach. Let's code it up. So this is our problem. I have found the same problem on LeetCode with the name maximum consecutive ones 3. The problem statement is same. The examples are same. Let's code it up, our solution over here. Okay, so I'm here. I forgot recording while I was coding it up. If you can see here, I just show solve, and before I didn't solve it, I forgot recording the video. So here we are, and let me code it up again. So let us calculate the length of the given array and equal to num start size, and we have to take the starting pointer. So start equal to 0, and we have to also keep track of maximum length of the window. So maximum length variable, and also we have to keep track of number of zeros in our current window. So let us take another variable zeros for that. Initially everything will be 0, initiated to 0, and we have to take a end pointer which goes through the array. So I n plus plus. Okay. Now if numbers of n is equal to 0, then we increment the zeros count and we check if current window is valid. If it's not valid, we make it valid. We increment the start pointer until it's valid. So how do we check that? We check if zeros count is greater than k. If it's greater than k, then it's invalid, right? Now, if numbers of start is equal to 0, then we have to decrement the zeros count. Otherwise, and then after decrementing the zeros count, we have to increment the start pointer. And now, after doing this loop, after completing this loop, our window will again become valid. So we take the length, we calculate the length, and then we update the maximum length. Maximum length equal to maximum of maximum length comma. How do we calculate the current length of the window? End minus start plus 1. And finally, we return the maximum length. Looks good. Let us run the code. Passed all the sample test cases. Let us submit it. It passed all the test cases. So what will be the time complexity of this approach? As discussed before, the time complexity will be O of n, and space complexity will be O of n of 1, because we are not using any other data structure. We are using only constant variables. So that's all for this video. I hope you have understood today's problem and solution. If you did, make sure you hit that like button and subscribe to Coding Charms for more problem solving content and interview related content. So till the next video, keep practicing. Take care. Bye bye.